All right, so our next section is going to be 3.6 absolute value functions. So when we're dealing with absolute value functions, we're talking about something where we have the positivity of a quantity being guaranteed. For example, if I had a very simple absolute value of x equals 2, whatever this value x is, it's going to make it become positive. So there are two values that could have given me that. It would have been obviously x equals 2, or if x had equaled negative 2, then I obviously, after the absolute value is evaluated, I get a positive 2 here. Okay, so a couple things we have to take into consideration, that when we are solving, whatever quantity is inside of this absolute value, once I have this isolated, I need to account for the fact that it could have been positive or that it could have been negative. So we're going to have to split this into two cases. So one of the other things that we're going to look at is we're going to have some absolute values that are going to have no solution. So one thing we're never going to be able to have is, say, the absolute value of x equaling a negative value, like negative 5. Doesn't matter what value I put in there. When I evaluate the absolute value, it's going to come out as a positive value. Thus, this has no solution. So let me come back to the definition here. So if I have real numbers a and b, then the absolute value of a equals b, with b being greater than or equal to 0. And we'll have solutions a equals b and a equals negative b. If b is strictly less than 0, then we're going to have no solution for the equation absolute value of a equals b. All right, so which one of the following has no solution? I can't tell right now. It has to be isolated before I can make that determination. So here on the left, if I add 15 to both sides, I would have 25 equals negative 3 times absolute value of 2x minus 4. And if I divide by negative 3, I would have negative 25 thirds equals the absolute value of 2x minus 4. Okay, now I've isolated my absolute value and it's set equal to some number that is negative. As soon as I have an absolute value that's isolated and that value across from it is either equal to a negative, or it could be less than or equal to a negative as well if we're dealing with inequalities, and we're going to have a no solution. In my other case here, if I add 35 to both sides, here I get 30 equals 2 times absolute value of negative x, and when I divide by 2, I get 15 equals the absolute value of negative x. This one is going to give me solutions. I'm allowed to have a negative x inside here, all right? It's going to be negative 1 times whatever that quantity is, x, and then we're going to evaluate the absolute value. We're good to go here. This is going to have solutions, okay? So let's come down here. Let's take a look at a couple, and let's find a couple of absolute value solutions. So starting with this one here, I've got negative 3 equal to 5 times the absolute value of 2/3 x minus 4/5 and minus 7. So again, I need to isolate my absolute value before I can do anything else. So we're going to add 7 to both sides. This is going to give me 4 equals 5 times absolute value of 2/3 x minus 4/5. I'm going to divide both sides by 5, which is going to give me 4/5 equals the absolute value of 2/3 x minus 4/5. So now I can split this into two cases. The first case is going to be my positive case, right? And again, what we're going to manipulate or change is this value opposite my absolute value. So my first case here, we're going to have 2/3 x minus 4/5 equals 4/5, right? I'm allowing this value to still be positive. Right? My second case, what's inside my absolute value is going to stay the same. It doesn't change, right? I still have 2/3 x minus 4/5, but now I want to account for the case that whatever was opposite the absolute value has the opposite sign. So I'm going to multiply by negative 1. In this case, it's a single term, so I'm just going to put a negative in front of it. But if I have a quantity over there, right, or some algebraic expression, I have to distribute a negative to all terms opposite my absolute value. So from here now, I'm just going to solve each case. So when I add 4/5 to both sides here, I'm going to have 2/3 x equals 8/5. In the second case, when I add my 4/5, we're going to have 2/3 x equals 0. So when I multiply by my reciprocal, 3/2, I'm going to have x equals, and we can do a little reducing here. So I'm going to reduce this to a 1 and a 4 to make my life easier. And we're going to get 12 fifths. And here we're going to have x equals 0. Right? Had you not reduced that ahead of time, you would have had 24 tenths, which are both divisible by 2. You still get 12 fifths. All right? So my two solutions here are x equals 4 or 12 fifths and x equals 0. All right? And actually, I should really put it or here, not an and, because it's the first solution or the second solution that satisfies my equation. It's not an and. Okay? When we're graphing absolute value, okay, for the most part, they're going to fall into a nice, neat pattern, nice, neat form where we're going to follow our graph shifting. Remember, y equals a times absolute value x minus h plus k. So here my a value is -5. My vertex is going to occur at -3, 8. So at -3, 8, I'm going to have the vertex of my graph. It's going to be flipped upside down. It's going to have a slope of -5 because it's absolute value. And we're going to have a graph. It's going to look something like this. Okay, easy peasy, nothing to it. Should be pretty straightforward, and again, from graph shifting. Now, let's throw one other thing into the mix. Remember earlier, I had said we could have something y equals a times, I'm going to use f in general, f of bx minus h plus k, right? I can have a horizontal stretch or compression. All right, we're going to see that here. Once we start having horizontal stretches and compressions, things get a little funky. It sometimes becomes more of a pain to do it with graph shifting, and it's honestly easier just to generate an XY table. Okay, so my next example here, I've got y equals the absolute value of -2x plus 1 and minus 9. Okay? So remember that when this quantity inside equals 0, this is where the center of my graph, or where the vertex, is going to take place. So if I go to solve this, we're going to have 2x equals 1, or x equals 1/2. So this graph's going to shift to the right, 1/2 of a unit. But it's also going to compress by a factor of 2, all right? Remember that if this value, the b, was greater than 1, we're actually going to have a horizontal compression, okay? So my vertex here is going to be at the point 1/2 and -9. My b value is a -2, all right? So it's going to have flipped horizontally, right, and then compressed, okay? Normally you would have thought this would have gone to the right one, right? But then because of the negative here, so it really kind of went, to the left one. It really did kind of go to the left one, and then it flipped horizontally over the x-axis, okay? So again, the one thing that we can always do when we get something like this, if you're really not sure, pull up the graphing calculator, okay? Make your life a little easier. So here we're going to have the absolute value. So let's see if I can find that in our math menu. So the absolute value of -2x plus 1 and minus 9. And if I go and graph that, now we're going to have a graph that looks something like this, all right? And that really wasn't to scale. If you notice, my scale was different there. That's why it looks, not sure why that's not square. Let me see if I can make that a square window. There we go. All right, so now it looks compressed because we actually have a square window. So let me go back, because what I really want to do is generate the table. I'm not really sure why my XY table looks like that here. Let's change my table set. I want it to go by ones. actually for this. I think I wanted to go by 0.5. So now, here we go. All right, we're good now. And for you guys, if you do that table set, down here at the bottom was auto or ask. When it was an ask, I had to input each X value that I wanted for it to be generated for me. If you click that and change it over to auto, and it's just, you know, the nuances of learning a new app, you put it over to auto and it automatically fills it based on your table set. Normally I have the delta table or the change in X value set at 1, but for this, because we had a X value of our vertex at 1/2, I thought it was more advantageous to have that at 0.5. So if I take a look here, and again, I'm able to just by touching and dragging move these values. All right. So if we go to graph this, we already knew we had a point at -1, or at 1/2 -9, which was up here. All right. And then we have values, you know, at 0, -8. We have a point at, let's go to -1, -6, -2, -4, so on and so forth. Okay. And we're going to have points that look something like this. All right. This one here is not too bad. All right. But when you start dealing with horizontal shifts and horizontal compressions, sometimes it gets really messy, and honestly, it's just easier and takes less time to go ahead and generate the XY table. You have a graphing calculator available to you 99% of the time for this course, and use it to your benefit. Okay. My apologies that it did take a second there to work through an issue or two that first time I had actually generated a table with that app. Okay. Applications of absolute value. All right. So anything that has a periodic function, right, or repetition, we can deal with and model with absolute value. If there's a certain pattern that can be discerned, or if in engineering fields, we talk about tolerance, and in terms of tolerance, what we can have is, you know, maybe the diameter of a pencil has to be a certain amount, and it has to be within a certain range of a precise value. Okay, so maybe a pencil is supposed to be a 1/4 inch in diameter. Okay, and it needs to be within 1/64th of that 1/4 inch, or it's not going to meet the quality standards for one reason or another. We're able to model that with an absolute value inequality. Okay, so tolerance is that allowable change, right? So what we have, right, when we do a tolerance type problem like this, we're going to have our actual minus either the average or predicted. And by predicted, I also mean what it's supposed to be. So, you know, prescribed value for something in an engineering application as well. And it has to be within a certain tolerance amount. So less than or equal to whatever that tolerance value is. So the example I have here, right, and when we talk about tides, we know that tide comes in, water goes up, tide goes out, water goes down. It's all based on the lunar cycle and the moon and all the fun stuff that's going on there. Okay, we can actually model or look at the tides and write an absolute value equation. It's not necessarily going to give me the actual height of the tide at a specific time like we could with, you know, a sine or a cosine function. But what we can do is write an absolute value function that models this very well. Okay, so let's say measured at a pier in Ocean City, the depth of the water has an average value of 15 feet. Okay, so we have an average value of 15 feet, right? And that varies by 2.5 feet, right? Which would be my tolerance, my variable amount, right, from low to high tide. I want to write an absolute value inequality that describes this situation using that variable with a depth of D. okay? So if my tide goes, from high tide down to low tide, oops, and it's going to come back to high tide, and it's going to do something that looks like this, like a really junky sine function, okay? Here's my average depth. If my total variance here is 2.5 feet, that then means that my actual change from the average to high tide is 1.25 feet. Okay, so what I can do here, so my actual variance from average is 1.25 feet. So what we can then write here, and the actual is going to be my variable d, it's going to be my measured amount. So the depth at any time minus my average of 15 feet is going to be less than or equal to 1.25 feet. And again, that's going to account for my total from its min to its max from low to high tide. Okay, so this equation, this absolute value inequality, is going to represent our tolerance or variance for this particular situation. So what I would like you guys to do is on my next slide here, we've got a piston ring for a vehicle engine, has to have an outside diameter of 3.05 inches with a tolerance of less than 0.1% to ensure proper performance, right? You're not going to get compression if there's too large or too small of a gap. Well, I guess if it's too large of a gap. If it's too small of a gap, that piston's not going to be able to move freely within the cylinder, right? So I want you to write an absolute value inequality for this situation, and I don't want you to actually go through and I want you to solve it, okay? So if we come back up here, if I go to solve this, I have an absolute value inequality as a less than, so I'm going to make this a three-part inequality. I'm going to take this quantity on the right, I'm going to put it on the left with a negative 1.25, less than or equal to d minus 15, less than or equal to 1.25. And when I add the 15 to all three parts then, we're going to have, let's see here, we're going to have 13.75 less than or equal to d, less than or equal to 16.25. So the average depth at this particular pier is going to be anywhere between 13.75 feet and 16.25 feet. And I've realized I never actually put the instructions to solve it up here in this first application like I did in the second. So for the second one, for the engine piston, I want you guys to go through, I want you to try to write an absolute value inequality, and I don't want you to try and solve it. And we'll go over this tomorrow when we are in class. Last but not least, I want to be able to write an absolute value equation given a particular graph. So again, let me remind you of my general form. A times absolute value x minus h and plus k. So I am able to identify a vertex, h and k, here at the point -3 and 5. Now, in terms of my a value, right, I want to look, where do I go through exact points? Here, and obviously here at my vertex. So I want to draw like a little right triangle here, okay? And I want you to actually sketch in, so it's going down 2 and over 3, okay? So since it's going down 2 and over 3, you can think about the slope here, right? A then has to be negative 2/3, okay? My h and k vertex is going to be -3 and 5 for h and k. And I'm simply going to substitute in then, and we're going to have y equals negative 2/3 times the absolute value of x plus 3 and plus 5. All right. So again, when you have a problem like this for absolute value, it's pretty straightforward. Identify your vertex, find 2 points where you pass through exact intersecting points on your graph, on your grid, and go ahead and find the a value. When we start looking at writing equations of, this isn't linear, but ones that don't have linear halves, like an absolute value, so we start looking at this with in terms of quadratics, cubics, so on and so forth. We have to do a little bit more, but for right now, this is going to work for what we're doing here. All right, so go ahead, give that other tolerance problem a try. We'll go over that one in class tomorrow, and I will see you guys tomorrow morning.